Dr. S.S. Patil, Professor, Department of Civil Engineering, Walchand Institute of Technology, Solapur. So today I am going to discuss about a design of counterfort retaining wall, part 4. This is part 5. This is the last part. So in which I am going to discuss about counterfort design of a counterfort retaining wall. So this is the last one remaining. It is prerequisite to see the design of counterfort retaining wall part 1, part 2, part 3 and part 4 before going through this particular one, because this is the last one. The entire design of counterfort retaining wall was divided into 5 parts. This is the last part. Learning outcomes. At the end of this session, students will be able to analyze and design the counterfort of a counterfort retaining wall. This is an example. Design a counterfort retaining wall of height if the height of the wall above the ground level is 5.5 meter. SBC of soil Q0 equal to 180 kN per meter square. Angle of internal friction phi equal to 30 degree. And unit weight of backfill 18 kN per cubic meter. Keep the spacing of the counterfort as 3 meter. Coefficient of friction between the soil and concrete is mu, that is equal to 0.5. Adopt M20 grade concrete mix and Fe415 steel. So before viewing this particular video, kindly see this first video, part 1. It is proportioning and stability analysis of counterfort retaining wall, where we fix up the sizes of the different components, and then afterwards we do the stability analysis, then design of stem slab, then design of toe slab, then design of heel slab, and this is the last one, design of counterfort. So please see, this is the stem slab, this is toe slab, this is heel slab, and this is counterfort. And the counterforts are placed at 3 meter apart. The distance between the counterfort, these are the counterforts. So here the distance between them is 3 meter. So this is called heel slab. And the front one is stem slab. Now this is the pressure distribution over the stem slab. And this particular figure, this is the pressure distribution at the base. This is the pressure distribution at the base. And how to determine all these things we have already discussed in the previous videos from part 1 to part 4. And this figure I have shown to find out, to tell you about this depth. So depth is the perpendicular distance, that is, this is a counterfort which is having varying depth. This is a counterfort, it is having a varying depth. So therefore, this is the depth of the counterfort, which is the perpendicular distance from this particular line. This is figure 2. The next, we have already designed stem slab. I have shown you the reinforcement arrangement of that. We have designed the toe slab. So in the video number, part 3, we have designed this particular stem slab. In part 1, we have done proportioning and stability analysis. In part 2, we have designed this stem slab. In part 3, we have designed this toe slab. In part 4, we have designed this heel slab. Now we are designing this counterfort. Now the reinforcement are required for the beam action and for against separating forces in the horizontal and vertical direction. So for beam action, so this counterfort is nothing but a beam. So counterfort behaves as a T-beam. Counterfort behaves as a T-beam of varying cross section, cantilevering out of the base. Cantilevering out of the base. Please see here. So this is a T-beam. This is a T-beam which is coming out as a cantilever from base slab, which is coming out from the cantilever as a base slab. So I will just show you the previous figure. So this is a counterfort. This is of varying depth. It is here, you can see this is varying depth, and this is a stem slab. A portion of stem slab behave as a beam. So therefore this is a T beam. This is a T beam. So a portion of stem slab and this particular beam or counterfort of a varying depth, that is a T beam. So T beam, which is figuring out from where? It is coming out from base slab as a cantilever. It is coming out as a beam from the cantilever from the heel slab, and it is having varying depth. This is the concept of design of counterfort. So now inclination of the counterfort we have determined from that figure. It is tan inverse of 6.5 divided by 2.9, that is 66 degree. So depth of counterfort D from the beam for the beam action at a junction as shown in figure 2, it is 2.9 times sin phi. So that will give us 2.48 meter. So I will just show you the figure wherein it is shown. This is the figure. So this is depth. This is the depth. So it is determined by taking this particular triangle. So now this is a review question. Counterfort behaves as a T-beam of varying section, cantilling out of the base. Is it true or false? Can you guess the answer, please? The review answer is it is true. It is a cantilever. It behaves as a counterfort behaves as a T-beam of varying cross section, cantilevering out from the base. Now this is design process. So the maximum bending moment on the counterfort, it is K gamma H cube divided by 6 into L. So that is the maximum bending moment that is at the face of the counterfort, which you will get. So this is the maximum bending moment. Therefore it is 1/3 of K is 1/3, 18 into 6.5 Q divided by 6. So into 3, that will give us the bending moment. So this particular bending moment mu, this is the bending moment which is induced due to the lateral pressure. This is bending moment induced due to lateral pressure. So mu we have calculated. It is 1.5 times m. So it works out to be 1235.8 kilonewton meter. So area of steel required is given by, again we have used G1.1b. mu is equal to 0.87 Fy ASTD into 1 minus AST Fy upon FCKBD. So by using G1.1b, we have calculated the area of steel required for the bending moment of a varying cross section beam, counterfort beam. Now area of steel was out to be 1339 mm square, but the minimum reinforcement required is 0.85 BD upon Fy as per IS 456-2000. So therefore it is 0.85. B is 300 because width of counterfort we have taken 300. D is 2648 which we have calculated. So divided by Fy 415, it works out to be 1627. Minimum steel works out to be more than design steel. Therefore we have to provide minimum steel. So therefore provide 4 bars of 25 mm diameter. So AST provided, it is 1963 mm square. Now the horizontal ties, considering bottom 1 meter height of the stem, maximum pressure to be transferred from the stem beam, that is the total pressure minus 3 minus 0.3, that is the spacing minus 0.3, it is 105.3. So factored force, it is 1.5 into that particular pressure, it is 158 kilonewton. Area of tensile steel required, it is this particular force divided by 0.87 Fy. So this will be the area of steel required. So therefore provide 10 mm bars at a spacing, these are stirrups, at a spacing area of 1 bar into 1000 divided by AST, that it is just, so it gives us a spacing of 170 mm center to center. So that means The horizontal ties will be at 170 mm center to center, 10 mm bars. And vertical stirrups. The vertical stirrups, so near the end of the heel slab, downward force, it is 97.8 kilonewton per meter square. So factored value is 1.5 times of that. So steel required will be 406 mm square. So provide 10 mm diameter, again stirrups, which will give us a spacing of 193, say 190 mm center to center. So we have designed horizontal and vertical stirrups. Now this is the reinforcement provided. So these are the vertical stirrups, 10 mm diameter, 300 center to center, and these are the horizontal stirrup, 10 mm diameter, 190 center to center. So this is, and here you will get 4 bars of 20 mm diameter tall, that means along this particular inclined face. So this is your main steel, and this is in plan, and this is the elevation. So this is how we have to design the counterfort of a counterfort retaining wall. So these are the references used for the presentation. Thank you.